All right, let's look at this problem here. A box of mass m initially at rest is acted upon by a constant applied force, Fa, as shown in the figure to the right. The friction between the box and the horizontal surface can be assumed to be negligible, but the box is subject to a drag force of magnitude kV, where v is the speed of the box and k is a positive constant. Express all of your answers. So looking at this, we're talking about a drag force and a magnitude Fa. So this is a force problem. First step in solving any force problem is to draw your free body diagram. So we'll draw weight down, normal force being up. We have Fa to the right, and then we also have this Fd to the left, because it's a drag force, so it's opposing the motion. Right, but do not solve a differential equation. And that's what this little video is about, is a differential equation. What in the world is a differential equation? That could be used to determine the speed of the box as a function of time. And it says if you need to draw anything extra, you can do that, but don't add anything to it. All right, so differential equation is just a regular equation. In this case, we're talking about forces. So step one when dealing with a force problem is to draw a free body diagram. What's step two? Get your net force from that free body diagram using Newton's second law. And for Newton's second law, we have a phrase, the stuff that makes it go minus the stuff that holds it back equals ma. Excuse the noises. So what is making this go? It is Fa. And what is holding it back? It is Fd, the drag force, and all of that equals ma. We don't care about the vertical here because Fn equals mg, they cancel each other out. This box isn't sinking or anything weird like that. And there's no friction going on, so that's why we're not including it. All right, so Fa minus Fd equals ma. Fa, we don't know what that is. We do know what Fa is. Or, excuse me, we do know what Fd is. Fd is kV equals ma. Okay, so under normal circumstances, we would just stop right there and we would say, boom, there we go. There's our equation. We can solve for what Fa is, or we can solve for whatever k is, if we wanted to figure that out. But what this question is asking us is we're looking for velocity later on down the road. For right now, it says write but do not solve a differential equation. This is not a differential equation. A differential equation has some notation of a derivative being taken. So we have v here, and we have a here. I'm going to ask myself, is there a relationship using a derivative between v and a? Yes, there is. I know that a equals dv dt, the slope of a velocity versus time graph. So now that I've added in that differential term, remember this d right here means differential velocity or changing velocity, very, very small change in velocity. Fa minus kv equals m dv dt, differential equation. That's it. That's how easy it is. So as long as you're good with, start with free body diagram and then do the stuff that makes it go minus stuff holds it back, plug in to figure out the forces that make it go and hold it back, and then just change one of your variables into a differential equation by substituting in any of the derivative that you happen to know. We want v and a to have this relationship because instinctively there is a relationship there between velocity and acceleration. So because of that relationship, we can now say, well, as our velocity is changing, here's the actual equation. This equation using algebra is constant, and then constant acceleration, and then this one here allows for changing acceleration because of the derivative.